Hey there, this is Mrs. Sharp. For those of you who will not be here today, Friday, I thought I'd give you a jump start on catching up on some of these notes we're going to take today regarding some 6.1 and 6.2 organic chemistry. So here we go. This is the learning target in 5 bullet points. 2 of them were review. We did those yesterday, and we will skip right past that and launch into the definition of organic chemistry. We learned this last year, way at the beginning of the year. The study of carbon-containing compounds, which is a pretty broad topic. Carbon compounds are really based on what we call carbon skeletons or even backbones, which are these long chains or rings of carbons connected by covalent bonds. So in addition to a skeleton, we can call these backbones. So just add that here. This is not something that I want you to have memorized, but I just thought it was interesting. Considering the broadness of organic chemistry, there are 10 million known organic compounds, so real carbon-containing compounds that would be studied underneath this little umbrella. Big umbrella, I guess. Let's talk about some orbital hybridization. Let's talk about the electron configuration for carbon. If I were to write carbon's 6 electrons into an electron configuration, from last year I would say that it would be 1s2, 2s2, 2p2, which would give me 4 valence electrons in the second energy level. If I were to draw the orbital notation for that, just the valence electrons, in 2s I would have 1 orbital and there would be 2 electrons. In 2p, there would be 3 orbitals and 2 electrons spread out in 2 of the 3 orbitals. Now remember, the 2s orbital is going to look like a sphere. The 2p orbitals are going to look like peanuts. 1 in each plane, so the XYZ plane. All right, well, all that stuff that I told you about the orbital shapes, for carbon is not entirely true. So for carbon, being the way that it is, with the 2 valence electrons in the p and the 2 valence electrons in the s, carbon does what we call orbital hybridization. So what it does is it takes these 4, so it takes the 2s, 1 2s, plus 3 2p orbitals, and it makes 4 what are called sp3 orbitals. So these are hybridized. So these 4 all together mold into these sp3 orbitals. So instead of this, we get sp3, 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 and sp3. So the 4 valence electrons go in each sp3 orbital, 1 apiece, which means you can have 4 bonds for carbon. In this situation, the way you would have drawn it is you would have had the 2s and then the 2p. So you would have only had 2 places really to bond because this would have been a lone pair. So this hybridization makes it much easier for carbon to make 4 bonds. These sp3 orbitals, by the way, are sort of a hybrid of the 2 shapes. So instead of the peanut and the sphere, we get sort of a big lopsided peanut. And then they can overlap, which leads to a tetrahedral shape. Because if you imagine bonding overlapping here, for electrons to get farthest away from each other, they would sort of have to push each other away into this tetrahedral shape. So what's the big deal about carbon? Why carbon in this huge organic chemistry field? The consequences of sp3 hybridization are that carbon can make up to 4 bonds. We just said that, which is a big deal. That's a lot of bonds for one little atom. Carbon can bond with itself, which is also a big deal. That leads to those carbon backbones that are really long. And it can make a variety of carbon backbone shapes. For example, there can be straight chains of carbon, branched chains of carbon, rings of carbon. That gives us a lot of options, and each different one gives us a unique function as well. So those are 3 reasons that carbon is so awesome that it gets its own branch of chemistry. Plus, one thing that's not mentioned on here is that it's the basis of life. So many macromolecules in your body and other living things are based on carbon. Without it, we wouldn't be here. Sort of a big deal. Okay. Here's just some examples of those shapes. So right here, you have what's called a straight chain. And see the carbon backbone, carbon, 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 carbon. Here you have a branched chain. So it's just like a straight chain with another chain coming off. And here you have a ring shape. And these can get much more complicated than what you see here. Just wanted to show you. Speaking of complicated, there you go. I'm sure some of these you talked about, especially if you had Mr. Nikolai. This is diamond, so carbon connected to carbon. This is graphite. Carbon's connected to carbon in like these thin layer sheets. Letter C looks like diamond again, but I'm not quite sure. This might be charcoal, just slightly different. These are your fullerenes or buckyballs. This is just kind of amorphous carbon all lumped together. And this is a carbon nanotube, which are starting to become a huge field, is this nanotechnology, nanotubes. You can see it's kind of a hollow structure. So some cool stuff to do with carbon. This is the structure for Vicodin, so I just wanted to show you the complicated ring structure here that you have. So that's the basis of, and you can see that it's 2 complex ions, a positive cation ion with the ring structure, and an anion over here, which is a hydrate. So that's Vicodin. And let's talk about some hydrocarbons. When we first start to talk about organic chemistry, we focus on hydrocarbons, and those are not atoms, but compounds containing only hydrogen and carbon. So just those 2 things, nothing else, hydrocarbons. Make sense? Hydrocarbons. So how we get hydrocarbons are through what's called the fractional distillation of crude oil. All pure hydrocarbons contain nonpolar bonds, so as molecules are nonpolar with weak intermolecular forces. Now to draw you a Lewis structure, this is ethane. Well, let's do propane, 3 carbons. So if I were to draw that, all of carbon's 4 bonds would be attached to either another carbon or a hydrogen, so it's a hydrocarbon. And every single one of these bonds has a difference in electronegativity that's very small. So they would all be nonpolar bonds, which means the electrons are not moving in any one direction in this molecule, which means the molecule is not sticky. There's not a sort of positive or a sort of negative end to this molecule, which means its IMFs, or intermolecular forces, are very weak. And you know that because at room temperature, propane is a gas, so it has a tendency not to stick to itself, but just kind of float away from each other. This is Alma, and the reason I put this isn't here anymore, but when I went to Alma, there were these huge, massive towers and a lot of pipes and whatnot, and these were called fractionating towers. And in Alma, there was a huge total plant. And what they did was distill crude oil into smaller hydrocarbons through fractional distillation. So this is how we get things like gas for your car, and jet engine oil, and wax, and methane gas, and all the different things that we need, that we use, come from the fractional distillation of crude oil. This is an example of a fractionating tower, so I just wanted to show you how this works real quick. this is the column, so this is that tall structure you saw. And what happens is that crude oil comes in over here and gets heated up really, really hot. When that happens, it separates, and I know this is kind of hard to see, it separates the different hydrocarbons based on their mass. Get rid of this here. This says C5 to C9, C5 to C30, C10 to C16, and you can see that the number of carbons is going up, so their mass increases. It says fractions increasing in density and boiling point. That means they're getting heavier or denser, which means their boiling point is increasing because they're heavier, so they're harder to lift up into the gas phase. It takes more energy. So you can see that these really light ones would boil pretty quickly up here, and this is your methane, propane, and that might be liquefied petroleum gas. And a little heavier, we've got gasoline coming out up here around 70 degrees. That's usually 7 or 8 carbons. We've got kerosene down here, paraffin oil. Here's your diesel, a little heavier. Here's got our lubricating oils. Now we've got things like boat fuel. And then down here we've got stuff like asphalt, essentially. So that's how they separate the components. It all is kind of mixed together in this gross sludge. And so they heat it up, and then depending on how high in the tower you go, you should be able to collect and separate those different components. It's pretty cool and pretty gross. And it stunk real bad. So next we're going to talk about some different types of hydrocarbons. And we're going to predominantly focus on this side. I think this chart is excellent. So I have a sheet. If you're not here today, you obviously don't have that sheet, but I will give it to you when you come back. It looks a lot like this. I couldn't find the exact one electronically, but we have these aliphatic hydrocarbons, which just means they're not going to contain a benzene ring, which you don't know what those are anyways. So hydrocarbons, for now, we're going to also know them as aliphatic, and we're going to focus on alkanes in the next segment. So I'm going to pause it there. That's part 1. And then we will go on to